The vast oceans of our world cover nearly 3/4 of the planet. They are the birthplace of weather systems that sweep across our continents. They are also a vital source of mankind's food. Welcome. I'm Zan-Misέλ Κουστώ. To understand the Earth, we need to look at the sea. This study is called Oceanography and allows us to understand the world beneath the waves. At Scripps Institute of Oceanography in La Jolla, California, scientists are learning about the wind and ocean phenomenon known as El Niño, and they also monitor the increase of gases suspected of causing global warming. Join us as we follow this group of scientists as they collect information regarding the world's oceans. Next on Stories of the Sea.
Our planet, the Earth, is misnamed. 72% of the Earth is covered by water, with an average depth of over 2 miles. The continents are in reality just islands in a single ocean which covers the planet. The atmosphere is another ocean, an ocean of air that covers our world. These two oceans, one of air, the other of water, are intertwined in a complex relationship. These two systems are a coupled environment which affects each other directly. Only recently have scientists begun to understand the scale and complexity of the interaction between the atmosphere and the ocean. It's difficult to separate how one system affects the other. What is clear is the ocean and the atmosphere work together to moderate the heat which the Earth absorbs from the sun. The oceans capture massive amounts of solar radiation, then release this heat slowly, warming the air above. The ocean and the atmosphere work together as a heat engine that converts the energy of sunlight into moving masses of winds and currents, which push the ocean thousands of miles. In turn, this vast movement of water warms the northern latitudes of the planet. The best example of this is the mild weather of the British Isles. A current from the Gulf of Mexico streams northward and warms the northern atmosphere enough to allow palm trees to grow in Scotland. Although scientists do not fully understand the complex interaction between the physical forces at work, during the last 100 years, they have attempted to learn more about the oceans and how they affect our planet. The study of the oceans, the world beneath the waves, the interaction between the sea's surface and the atmosphere, and how the atmosphere is affected by the sea, all fall under the realm of oceanography. The ancient Egyptians, Greeks, Phoenicians, and Romans all ventured out on the oceans. With meager knowledge, they carried on commerce and trade, discovered new lands to conquer and colonize, and fought battles on the Mediterranean Sea. They were the first to use the North Star to navigate. They correlated the effects of tidal changes with the phases of the moon. The Greeks investigated marine life and understood the usefulness of coral as a medicine. The early Romans used seaweed to heal wounds, burns, and scurvy. The great thinkers from the ancient world have passed on their knowledge and experience for later generations to build upon. It wasn't until the Renaissance, the age of discovery, that interest in the oceans was rekindled. Columbus, Magellan, and Prince Henry the Navigator collected information on currents, weather, and marine life as they explored the oceans of the world. The history of modern oceanography is a story of scientific discovery and technological innovation which began about 200 years ago. Captain James Cook is known as one of history's greatest seamen and explorers, but he was also a scientist, and in the first scientific expeditions in history, Cook accumulated large amounts of information during 3 visits to the Pacific Ocean. In 1768, Cook sailed to the Pacific, accompanied by an astronomer, 2 botanists, a landscape artist, and a painter of natural history. He made observations of wind, currents, water temperature, and took depth soundings up to 200 fathoms during his voyages. However, in spite of the accomplishments of Cook and many other scientists, there was little attempt to organize the information and put it to use. The first American to use practical information about the ocean was Benjamin Franklin. As Postmaster General for the American colonies in the 1750s, he noted that mail coming west from England took weeks longer to arrive than mail traveling the same distance east back to England. While on a voyage to Europe, Franklin lowered a thermometer overboard and took scores of water temperature readings. The temperature showed that a stream of warmer water traveled up along the coast of America. With the help of his cousin, a whaling captain, Franklin learned of a warm water current welling up from the Gulf of Mexico. Franklin used his observations of currents, sea color, and surface temperatures to sketch the course of the Gulf Stream on a chart of the Atlantic. Merchant sea captains took notice of Franklin's chart. For years they had battled against it, but with Franklin's chart, they began to make the Gulf Stream work in their favor. In just a few years, Franklin's map would later aid French and American captains carrying arms and supplies to colonial troops. Knowledge of the oceans took a great leap forward in 1872, when the research vessel Challenger sailed from Portsmouth, England, on an epic voyage of scientific investigation. The Challenger's mission was to study life and conditions above and below the waves. The ship was fitted with a state-of-the-art laboratory to examine specimens. 6 scientists, using the most modern instruments of the time, took temperature and depth readings around the world. Never before had an expedition produced so much information about the oceans. During the 3.5 year, 68,890-mile voyage, the Challenger discovered a number of new life forms, charted surface currents, and made extensive deep-water temperature profiles. Today, the Scripps Institution of Oceanography is known as one of the most important centers in the world for research and graduate education in the marine sciences. Established in 1903 as an independent biological research laboratory, Scripps became part of the University of California in 1911. The scope of its research programs includes physical, chemical, geological, geophysical, and biological studies of the ocean. Scripps' fleet of research ships travel the world's oceans on expeditions designed to gather a variety of oceanographic data. Scripps has one of the finest global climate research centers in the world. Established in 1989, the Climate Research Division studies natural climate changes, the buildup of greenhouse gases in the atmosphere, and other global weather phenomenon. Scripps' research efforts use environmental information collected from around the world to develop models using supercomputers to forecast El Niño-type events. In June of 1982, meteorologists noticed a dramatic 6 to 10-inch rise in the sea level in the mid-Pacific. By late summer, Indonesia was in the grip of a drought. In Australia, thousands of acres of farmland were turned into desert by a relentless heat wave. Soon, suspicions that something strange was happening on a very large scale was confirmed. At the same time, other parts of the world were experiencing catastrophic flooding. The coasts of Peru and Ecuador suffered 300 times normal annual rainfall, and the worst floods in the century. Scientists noticed a pattern and traced a convoluted trail of cause and effects relationships back to their source. They blamed the global disaster on a warm water current that intruded into the waters along Peru. This condition warmed the ocean temperatures along the equator and shifted wind patterns covering a quarter of the globe. The phrase El Niño, Spanish for the child, was originally coined by fishermen referring to the warm water phenomenon appearing off the coast of Peru around Christmas time. Climatologist Tim Barnett has been charting El Niño's effects for 20 years.
El Niños are the largest, most significant natural climate fluctuation on our planet, and they affect literally billions of people, mostly adversely. They cause droughts and therefore famines, as well as excessive rainfall and flooding.
The weather of 1982-83 was devastating. The drought spread to India, Sri Lanka, the Philippines, Hawaii, and Mexico.
What happens during an El Niño is that the surface waters of the central and eastern tropical Pacific become warmer than normal in a band that stretches east to west across the entire ocean, more than a quarter way around the Earth. This change in ocean conditions is associated with massive changes in the circulation of the atmosphere over much of the globe.
El Nino affects atmospheric changes over North and South America, pushing storm patterns away from their normal paths. This short-term climate fluctuation can cause drought over huge parts of the planet and affects billions of people. Changes in wind patterns alter the movement of the ocean, which in turn disrupts the winds. Scientists are still not sure what triggers the whole process. In the years since the huge 1982-83 El Nino, countries around the world have started research programs to study how the ocean and atmosphere interact to create an El Nino. Forecasting an El Nino event could provide information to minimize the negative impact to crops, environment, and people. Several Scripps research groups are working on a number of international experiments at several locations in the South Pacific. The tropics are the center of the action between the ocean and the atmosphere. It is where the Earth receives the most energy from the sun, which drives the atmosphere. One experiment, called TOGA, for Tropical Ocean and Global Atmosphere, and the Coupled Atmosphere-Ocean Research Experiment, called CORE, gathered data using automated buoys, surface ships, aircraft, and space satellites. Automated buoys form the backbone of the El Nino studies. These deep-sea giants are anchored to the sea bottom. They measure air, water, temperature, wind, and humidity along the equator. The data is transmitted by satellite to a laboratory, where it is entered into a computer. The computers then tell researchers whether conditions are ripe for an El Nino. Another experiment designed to measure ocean currents uses drift instruments that consist of a float which houses a computer, an antenna, and a battery pack that powers the unit for up to 2 years. The float rides on the surface and is connected to a long tubular sock. The sock is unaffected by the wind. It is held open by metal rings and has holes in its side to ensure that the device remains submerged in the water just below the surface. The computer logs the drifter's position and weather conditions while the sock hangs below. The drifter makes very accurate measurements of surface currents and transmits that data to satellites flying overhead. Another unique floating instrument is deployed by researchers to measure currents in the deep ocean. Each device sinks to a great depth for periods of up to a month, then automatically surfaces and radios its new position. Balloons released into the atmosphere collect information on the columns of air rising from the ocean's surface. These programs will provide for the first time highly reliable measurements of large-scale open ocean currents and circulation, critical to understanding climate.
The data collected during an El Nino event, sea surface temperature, wind speed and direction, solar radiation, and so on, are fed into computers and become part of the database of global climate history.
An experiment based on the island of Fiji studies the effects that clouds have on climate. The Central Pacific was chosen because ocean scientists wanted to know what happens as ocean temperatures increase. The experiment used aircraft flying at different altitudes to collect data on solar radiation. At the same time, research ships sailing along the equator collected data on surface temperatures, solar radiation on the surface, and the rate of evaporation. Each day, the planes flew several thousand miles and returned with volumes of data. Recording instruments were removed for analysis. A laser measured the altitude of the clouds while the planes flew at 60,000 feet. This month-long study was the most detailed study ever made of clouds and their relationship to warming the ocean's surface. Until recently, with the vastness of their subject, oceanographers have always collected information from mid-ocean using costly and time-consuming voyages by ship to retrieve the data. Satellites are the most significant data-gathering tools yet to be offered oceanographers. Finally, man can evaluate almost instantly all the complex features of the ocean environment. NASA's Topex Poseidon satellite, circling the Earth every few hours, can quickly scan huge areas of ocean. With a radar altimeter, they can measure warm water bulges in the oceans overnight. Using infrared imagery, satellites measure the temperature of the ocean's surface, revealing the location of warm or very cold water and how temperature affects currents. These are key clues to the arrival of an El Niño event.
By looking at what occurs before, during, and after an El Niño, we have an indication of how the global climate system reacts to abnormal heating.
At the Center for Clouds, Chemistry, and Climate at Scripps, Dr. Ramanathan studies planetary atmosphere.
Although clouds play a central role in regulating the temperatures of the planet, it's one of the most poorly understood phenomena in earth sciences. It is this uncertain role of clouds which is the fundamental source of uncertainty in our ability to make accurate predictions of global warming. We need to understand the internal structure of clouds. This information can only be obtained from airplanes or remotely piloted vehicles. This information can help us to unravel the effects of different cloud systems. By combining data on clouds with climate model simulations, it becomes possible for us to predict the role of clouds on the future climate. We already know enough to state that just a small change in the cloudiness can have a tremendous impact on the global warming and on regional climate changes.
A sophisticated computer data processing system takes millions of bits of digital information and then displays this information in usable form. Through a technique called scientific visualization, the data is translated to three-dimensional images, giving researchers a new way of interpreting clouds and the ability to create a model of the global climate. What emerges from these continuous calculations is a worldwide forecast of the ocean environment. Where once scientists did not even know when an El Niño was occurring, now they can monitor the tropical Pacific day by day.
Our goal is to try to predict El Niños a year in advance, and we're making really good progress on that goal.
The study uses ocean temperature data from 45 years of measurements collected by Scripps Institution. A sea surface temperature program, combined with a model simulating the Earth's atmosphere, gives scientists a possible look into the near future. The model is based on past relationships between the wind and sea surface temperatures, solar radiation, and sea ice variations. There are two parts in the prediction process. The first is predicting the ocean temperature, which is often a difficult task. The other is to determine how the ocean temperature will affect the atmosphere. Richard Somerville is head of the Climate Research Division.
To make our computer models more reliable, we need better measurements of the physical processes of the climate system, some of which are not well understood. That's why we conduct research programs to monitor and observe such phenomena as cloud formation, air-sea interactions, and global circulation patterns in the atmosphere and the ocean.
While scientific methodology and computer models of the atmosphere have replaced the guesswork of weather prediction, there remains a fear about the future. There are particular anxieties about the Earth warmed by the industrial release of carbon dioxide, methane, and other heat-trapping gases.
The greenhouse effect is natural. It keeps the planet habitable. The concern is that we people are changing it in ways we don't realize. That's why we have to do research and to monitor and understand changes as they occur. Only then can we supply sound scientific information as a solid basis for policy decisions.
Some scientists believe there is a link between recent El Niños and global warming. In the last 12 years, the world has experienced 4 El Niños, which is well above the normal 1 every 4 to 7 years. A large amount of the study is concentrated in a search for signs of global warming. Any major shift in climate could wreak havoc with crops and population. It has been suggested that global warming is to blame for the rash of major hurricanes that have hit Florida and Hawaii, and some of the worst flooding in centuries. While most scientists believe that these storms are natural, their intensity and numbers do have them thinking about the correlation between climate changes and global warming. In the mid-Pacific, French Polynesia was battered by 5 typhoons in just a few months. Normally, they experience one such storm every 50 years. Despite the use of supercomputers to create models of future weather conditions, in reality, they are as reliable as witch doctor's medicine. Scientists have come to realize that the moderate conditions of today have only existed 10,000 of the last 500,000 years. Marine biologist Dr. Elizabeth Bendrick.
Fish populations have large natural fluctuations in size over periods from seasons, years, decades, even centuries. These fluctuations are driven by a variety of physical and biological processes. In order to understand the impact of global climate change on fish populations, we will need to study these processes for a long period of time. Data on environmental conditions and preserved animals from previous years serve as important libraries of information about California's marine ecosystem. One long-term study has shown that the disappearance of the sardine from California waters was a combination of overfishing and changing ocean conditions. Long-term ecological investigations are essential for defining what is normal in the ocean and for allowing us to evaluate future changes. Understanding the structure and natural variability of ecosystems and the forces that influence them will allow us to determine whether future change is natural or due to human activities.
Whether the world gets warmer, colder, or remains the same, extremes in the weather is a certainty. Scripps Institution is engaged in a continuing effort to understand this last and greatest frontier of our planet. It is a quest for knowledge that will improve the quality of life for all mankind.
The pollution we release into the atmosphere might increase the greenhouse effect. If so, we must take whatever action is necessary to avoid this dangerous global warming. The implications of worldwide climate changes on society are huge. We must all try to find a solution to this problem now. Otherwise, we may leave our children and future generations with a global disaster we could have prevented. It is our responsibility to protect our sea and atmosphere. The very future of mankind depends on it. I'm Zan-Misélel Κουστώ, and this is just one of many stories of the sea.